Alright, this is going to be our second video on magnetic fields and magnetic forces. The video is going to map to section 27.3 from the text. We'll cover that whole section here. And so let's get into it. We're taking a look at magnetic field lines and magnetic flux. And so we're going to start off with looking at the field lines themselves. So as was the case for electric fields, we can represent magnetic fields with magnetic field lines. Okay, so here the field lines are going to emerge from the north poles, and they're going to re-enter the magnet in the south poles. But unlike the case of electric field lines, these lines don't start or terminate anywhere. They're all loops, right? So we can see from the diagram here that these loops go through the magnet, and they all form closed loops. Okay. So we can see here as they've described some of the features of the diagram here. At each point, the field line is tangent to the magnetic field vector. So we can see they drew on some of these magnetic field vectors. The more densely the field lines are packed together, the stronger the field is at that point. This is sort of just a qualitative way of understanding how strong a field is in one region versus another region of a magnet. Okay. At each point, the field lines are in the same direction that a compass would point. Okay, and so the field lines always point away from north poles and toward south poles. Okay, so we see it kind of looking like this. Okay. So that's what our magnetic field lines would look like. We have to remember, though, that unlike in the case of electric field lines, the magnetic field lines don't point in the direction that a charge would feel force exerted on it if it were sitting in this field, right? So first of all, a charge is going to need to be moving to feel any sort of a force, and where we had this equation here for the force felt by a charge in an electric field, we see that our force has to point in the direction of the electric field because there's only two vectors here. But in the case of the magnetic field, our force is going to point in the direction of V cross B, right? And V cross B is going to point somehow out of the plane formed by V and B, right? And so definitely don't confuse these magnetic field lines for the direction in which any sort of force would be experienced, right? So that's one key distinction between the magnetic field lines and the electric field lines. Let's now take a look at the magnetic field lines for some objects that we're going to be sort of interested in here. We're going to look at this case where we're looking at a C-shaped magnet first. So you can kind of envision that this is kind of a C shape, and there's only a small gap in here, so it forms like a really tight C here. And if we look at the magnetic field between the two poles, we're going to see that they're very, very nearly uniform, very much like we would see the electric field looking between the plates of a parallel plate capacitor, right? So we have very, very uniform magnetic field in here. So that's an interesting and potentially useful configuration of magnetic field that we might look at. The next thing that we're going to look at are the magnetic fields around current carrying wires. So first just a straight wire, and then what happens if we start bending this wire into loops. So we're not going to do anything with this right away, but this is certainly going to be a topic that's going to be coming up over and over for the rest of the course pretty much. We're going to be looking at these wires, so let's just get a sort of feeling for what the magnetic field kind of looks like, and then we'll talk much more about it in detail in coming videos. So we can see here in this diagram labeled B that if we have current running down this wire in this direction, our magnetic field lines are going to look like these loops around the outside of the wire. So it sort of forms these concentric circles around the wire. And we're going to see that there's another right-hand rule at play here. If you put your hand sort of face up on your right hand, sort of face up on the page or the monitor or whatever you're looking this thing on, and your thumb points in the direction of the current, your fingers are going to curl in the direction of the magnetic field. Okay, and that's kind of what we also see on this right-hand diagram. What we see here is we're sort of meant to imagine that the wire is running left to right, and the current is running across the wire left to right. And then we have the magnetic field coming out of the page towards us on the top and going into the page on the bottom here. So you can kind of imagine that these things are looping around the wire here, right? And this is, I've talked about this briefly before, but these, when you see these dots, that just means that the field lines are coming out toward you, and when you see these X's, that means that the field lines are going into the page away from you. Okay, so you can imagine again, you put your right hand sort of backside down on the page. Your thumb points in the direction of the current, and you can see that the magnetic field lines would be curving sort of upward and out of the page on the top, and then around and downward and into the page on the bottom. Okay, so that's what the configuration of the magnetic field around a current carrying wire is going to look like. If we take this wire and then we bend it into a loop, as we see here on the left, or we bend it into a coil by bending it a bunch of times, this magnetic field starts taking on some of the characteristics that we see here. We can kind of see that it's kind of running through the loop here and forming a bunch of concentric circles, and if you pile it all up, you're going to see sort of a very strong magnetic field coming through the center of your coil here. Okay, and here I'm just mentioning what these dots and crosses kind of are meant to signify. So we're gonna come back to these, and we're going to take a much closer look at these as we look at other stuff further on in the chapter and then in subsequent chapters. Okay, so now we're going to move on to take a look at magnetic flux and Gauss's law for magnetism. So we define the magnetic flux through a surface or through a closed surface in the same way that we did in, or maybe I should make a note of that. Closed surface. In the same way that we did for electric flux in chapter 22, right? So the result that we're going to have in this section could basically be discussed in the same terms and derived in the same way as we derived equation 22.9 from chapter 22 when we were looking at Gauss's law. So here, this equation that we see here, this 27.6, looks basically identical to the definition of electric flux, except we're just swapping all the E's that were electric fields for B's now, so they're magnetic fields. So all the same ideas hold. If you sort of had trouble following the electric flux arguments in chapter 22, if that's an area that you maybe didn't do so well on the term test or whatever, I would recommend you go back and take another look at that stuff, because it's kind of like a 2-for-1 deal here. If you understand one of them, you understand both, and it's very likely that questions like these will come up, maybe not even just once, but maybe twice on term tests or finals in the future, right? So equation 27.6 here is our magnetic flux equation. Our magnetic flux comes in SI units of what we call Webers, and 1 Weber is just 1 Tesla meter squared. Okay, so these Webers are going to be what we would use to describe magnetic flux, and they're just a Tesla meter squared. Okay, now Gauss's law. Well, first maybe let me scroll down. So if we remember back, Gauss's law for electric fields, so Gauss's law, the way we normally think of it, is written in the way that we see here. So this is equation 22.8. This is from chapter 22, right? So we remember that our electric flux was equal to this integral over the closed surface of the electric field dotted into our area vector, and it was also equal to the charge enclosed over our, well, what they call electric constant here, right? And so we can develop the same idea Gauss's law of electricity for Gauss's law of magnetism, right? But there's a key difference here. The key difference is that while you can have individual charges, you can have single charges, you can't have individual or single magnetic charges, right? You can have single electric charges, but not single magnetic charges. Again, this is the whole that there are no. This is the whole argument that there are no magnetic monopoles, right? And so if there are no magnetic monopoles, and if our electric field, or I shouldn't say electric, our magnetic field lines form loops, then there is no way to enclose any amount of net magnetic charge. You're always going to enclose either a region where all of your magnetic field lines enter and then exit your closed surface, or you're going to enclose a region where all of your magnetic field lines form loops, and so you're not enclosing any sort of magnetic monopoles, I guess is one way to say it, any individual single magnetic charges, right? And so you still have the same expression, right? You still have that Gauss's law for magnetism gives you this magnetic flux expression here, this integral that we have to do over a closed surface of B dot dA, right, where dA is our tiny chunks of area and B is our magnetic field, but it's never going to enclose any magnetic charge, right, or no net magnetic charge. It could enclose some magnetic charge, but it'll always cancel out, because no matter how we partition up our magnet, we're always enclosing an equal amount of south and north pole kind of thing, right? So you're always going to end up with a zero on this side of it, and really it may seem kind of trivial, but this is a pretty profound thing to say. Our total magnetic flux through any closed surface is always going to be equal to zero, and so Gauss's law for magnetism tells us that well, basically gives us this expression, right? We end up with this closed integral of this dot product always equaling zero. Okay. So I mean, if this is kind of hard to believe, you can kind of right away do the thought experiment. We can scroll back up to, let's say, well, I mean, any of these magnetic fields would do, but let's say we looked at this magnetic field. If you imagined some sort of region, you can pick any region here, and you drew a closed surface. Any region where you draw a closed surface, you're going to have the same number of magnetic field lines coming in as you have going out. Or if you choose some sort of large region, or you pick a region inside the magnet, again, you're going to have that same case. And if you're imagining enclosing magnetic charge, well, you're always going to be enclosing equal amounts of south and north pole, in a sense, because if you split the magnet, right, wherever you split it, you're always just making a new north and south pole. So there's no way for you to ever enclose a magnetic monopole. There's no such thing as a magnetic monopole. And so really, it turns out sort of, in a way, sort of obvious that you're going to end up with a zero on the right-hand side of this, right? And so this is, I guess that's just a long story of how this is Gauss's law for magnetism, and we just have to remember that the right-hand side is always going to be zero. Okay, we're never enclosing any magnetic charge, any net magnetic charge. Okay. So there's something that I do want to mention as far as these area vectors go. So if we recall our area vector, or our little chunk of area vector here, our infinitesimal area vector, from equation 27.6, and if we think back to our work in chapter 22, these little area vectors always point out of a closed surface, right? This was sort of thing that we talked about in chapter 22, that when we have a closed surface, our area vectors for those open surfaces which form the closed surface, let's say we're thinking about a cube or something. Maybe I can draw it here. We can think about a cube or something. Now, if we're just talking about one face of the cube, it's kind of up to us how we want to think about the area vector pointing. But we've decided that if we have a closed surface, let's say we have 6 faces of our cube and we stick them together, in such a way that we have a closed surface, well then there is a convention that we've decided on that all of our area vectors have to point outward, away from the inside of our closest surface. These would all be A's. I mean, there'd be different A's, right? But whatever, each surface will have its own A, and it has to point outside of our collective closed surface. Okay, but in the case of well, I mean, this is true for both, but in the case of our magnetic flux, and when we're dealing with these area vectors, when we're dealing with the magnetic side of things, we're going to more often want to look at open surfaces. So, for example, we're going to look at maybe open disks or something like that. And in this case, we're free to choose which direction we want things to point. But we're going to run into these surfaces more commonly in this section than we did previously. So we want to make sure that we understand that A, we are free to make the choice on which direction our area vector is pointing, but B, we have to make sure we stay consistent with that choice as we're doing the problem. So if you start off doing a problem and you need to calculate the flux through a surface, and you select this direction, let's say for the area vector, stay consistent, make that the direction for the whole problem. And then if you're doing the problem and you keep this pointing of your area vector as the direction you're going to keep for the whole problem, everything's going to work out in the end because you've been consistent with that choice. Okay, so always make sure you keep the same direction for your area vector. So really, that's basically it for this chapter. Not for this chapter, for this section, I should say. We want to definitely sort of refamiliarize ourselves with this idea of flux. This is our magnetic flux. It's basically the same equation as our electric flux. We want to remember Gauss's law for electric charge, and that there is an equivalent sort of idea for magnetic charge, but there is no such thing as a single magnetic charge, so we end up with a zero on the right hand side, right? So the key things to remember for this section, the things that we're going to calculate with, are going to be 27.6 in all of its forms, the same way we had it for the electric version of this. And we also want to keep in mind Gauss's law for magnetism, right? So basically the same idea we had for Gauss's law in the electric case, but with zero on the right hand side again. Okay, so we're going to move on. We're going to do a quick example here. There's only one example in the text. I may do more at the end of the chapter, but for now I'll just focus on what they have, unless I see any sort of deficiencies that I really want to point out. So we'll start off here. We have the figure below. We have this sort of perspective view of this flat surface with an area of 3.0 centimeters squared in a uniform magnetic field, B, which we can see here sort of indicated by the blue lines. The magnetic flux through the surface is given to us. It's 0.9 milliwebers, and we want to find the magnitude of the magnetic field and the direction of our area vector A. Okay, so let's start off. So what do we want? We want B, and we want the direction of A. So we want B the scalar. We just want the magnitude of our magnetic field. So we'll be able to get, and I kind of want to keep the drawings on the page. So I guess I'll move down here. This drawing B here is basically just them looking at this in a sort of side view, so we can see the 30 degrees is here. Our area vector could either point upward here like this, and so it would point like upward out of the sheet like this, and that would be at 60 degrees from the magnetic field, right? If this is 30, that's going to have to be 60. We can kind of see it pretty clearly here. Or it could also point at 120 degrees from the direction the magnetic field is pointing, but we're going to see that only the 60-degree version is sort of valid in this case, and let's take a look at that right away here. So maybe the first thing to write down, we're going to use this expression for magnetic flux. This is just one of the versions from up here. Yeah, this is just this one here, except that we don't need to worry about doing the integral. Why don't we need to worry about doing the integral? Because our magnetic field is uniform, so it's going to be the same at all points. So B is the same everywhere, and so phi is the same everywhere also. So we don't really need to worry about integrating over the whole thing. We're just going to integrate over dA, and when we integrate over dA, we just end up getting A, right? So it's just going to be the area that comes back from that integral. And so we can sort of use this, or we will use this to grab our B afterward. We're basically going to just reorganize this so that we have our magnetic flux over a cos phi. But first we want to decide on what this phi is, right? Phi could right now, by everything that we've talked about so far, be either 60 or 120 degrees. But we know that these values, the values of our magnetic flux, our magnetic field, the magnitude, and our area, these are all going to be positive values. Okay, and because of that, we're going to need our cos phi here to be a positive value, right? Otherwise, we're going to pick up a minus sign, and this isn't going to be true. So we need all of these to be positive values. This means that the cosine of 120 degrees is kind of out of the question, and that means that we need our cos phi to be greater than 0, and this means that we need phi to be equal to 60 degrees. Okay, and so this kind of answers part of the question. This is giving us our direction of our area vector, and if we then take the values that were given up here, 3 centimeters squared and so forth, we can substitute these values in here and solve for B. So that's what I'll do here very quickly. I'll just rewrite it one more time. A cos phi, and so this is just going to end up being 0.9 times 10 to the minus 3 Webers over 3 times 10 to the minus 4 meters squared times cos 60 degrees. And if you do that calculation, you're going to end up finding 6 Teslas. Okay, so we have a magnetic field with a magnitude of 6 Teslas, which is a pretty significant magnetic field. Okay, so that's the only example I had set up for this one. So in the next video, we will move on to section 27.4. I'll see you guys in the next one.